All right, this is a review of problem 2B.6, flow of a film on the outside of a circular tube. So that's this section here. Um, we're going to assume Newtonian fluid, set up a momentum balance over the shell thickness delta R in the film. It's like this here, as shown in the figure. Note that momentum and arrows are always taken in the positive coordinate direction. So that would be this direction, high to low. Yeah, so the first part is just asking for the velocity distribution. So let's get to the problem then. So for this problem, there's going to be a pressure gradient and a velocity gradient, and the pressure is going to be due to gravity. And wait, does that make sense? No, sorry, never mind. There isn't going to be a pressure because the liquid is exposed to oxygen or exposed to air throughout the whole falling part. So there's not going to be any pressure term. If this was a pipe and the liquid was actually pushing against something like a pipe, there would be the pressure term. But since it's outside and open to the air, there's going to be no pressure gradient. So this this term is not going to be relevant. But momentum flux in the ZR direction is going to be relevant. So since the momentum flux in the ZR direction is going to be relevant, we really only need this AR face, because that's the face. It's the VZ due to the R direction, so we need the area in the R direction, because this is the VZ. This is going to represent the VZ in the R direction. This is going to be the important term in this equation. So AR is the radial direction. So when you're like looking at the cylinder, the face that the radial direction is perpendicular to is the face that's just like basically the outside of the cylinder. So it's just like this whole face that is highlighted, and that's 2 pi times r, which is this length, times L, which is the height of the cylinder, and that's where that comes from. And then AZ, it's not really relevant for this problem, but in the Z direction, it would be the face that the Z direction is perpendicular to, and that would be a thickness delta R and a length 2 pi r, because this length here is 2 pi r. And there's some complication to that formula, but it's not really relevant. Yeah, it's pi r plus delta r squared, because it's minus delta r squared, and that's because this is r plus delta r or this is r plus delta r, and this is r right here. So the thickness of this is this dimension here is does that make sense? It's the big circle minus the small circle. Yeah. So like this circle, this circle including the middle area minus just the middle area. So it's the area of a circle pi r squared minus the area of the smaller circle, or the area of the larger circle pi r plus delta r squared minus pi r squared minus pi r squared. So if you multiply that out, this cancels, and this is left. And this term also cancels because delta r squared is infinitely smaller than delta r, and that's because delta r is an infinitely small value. So if you square an infinitely small value, like I write here, it's going to be like infinitely smaller than the infinitely small value, basically. So, I mean, you could just read this. It basically says that with actual numbers. So now we're applying this AR face to the momentum in the RZ direction. So this is momentum in minus momentum out plus the gravity term, which the gravity term is multiplied by the whole volume of the solid. So that would be like this whole, the volume of this. So it would basically just be you mash up these terms. 2 pi, you basically just multiply this by L. It's the volume of the differential. It's the volume of the differential volume, which obviously that makes sense. 2 pi r, delta r, and L, and that's just, you're basically just multiplying this area by L, and that's the differential volume. L is just the height of this cylinder, and that's where that comes from. 2 pi r delta r, which was derived from this whole formula, and then just multiply that by L. Yeah, and so gravity acts upon the whole volume, so that's why you're multiplying gravity by that, and 2 pi L by the R is in the parenthesis because momentum flux in the RZ direction, or RZ momentum flux, it has to do with the velocity in the Z direction that changes in the R direction. So since it changes in the R direction, we're putting the R in the parentheses because we're not going to divide that out when we divide the volume. So we're going to divide the volume, but without the R. So that's why I put that in parentheses preemptively. So now we're going to define the momentum fluxes, momentum in the ZZ direction, which will end up being 0 because the pressure does not depend on Z, and momentum flux in the ZR direction. So I'll just skip this because it's not really relevant, because ZZ direction, momentum flux equals 0 because this P is not dependent on Z. So pressure at this value and the pressure at this value will cancel out and equal 0. So momentum flux in the ZR direction equals tau ZR plus rho VZ VR, and that's from, it's from right here. Momentum flux in the X in two different variables. So this is XY, this could be XR, this could be theta R. This is just it's two different variables, or two different symbols. So this is the same symbols, this is different symbols, and the only difference between these two is that when you have the same symbols, you have a velocity. So if you look at up here, it's pressure times the sigma, and the sigma equals 1 when the symbols are the same, and the sigma equals 0 when the symbols are different. So that's why when the symbols are different here, the sigma equals 0, and then the pressure just disappears from the expression. So yeah, momentum flux in the xz direction is tau xz plus rho vx plus rho vx vz. Yeah, that's kind of just a long-winded extra explanation. So yeah, momentum flux is just rho, or what is this? Tau zr or xz, or zr, zr, not zx, because it's the radial direction of cylindrical coordinates. And rho vz vr equals, this term goes to 0 because there's no radial velocity. And so momentum flux in the zr direction equals tau zr, which equals negative mu dvz dr. And that's because if we go to table B1, tau zr equals negative mu dvr dz plus dvz dr, and dvr, or the velocity in the r, there's no velocity in the r, so this term goes to 0. So tau zr is just negative mu dvz dr. So yeah, that's where we got that. And so we have this expression with these new derivatives inserted for the momentum fluxes. So we got this, and we're just plugging that definition into this equation here. And now we are going to divide by 2 pi L delta R, and we're not dividing by, so this is just the volume minus, or just without the R, and that's because this momentum flux depends on R, so we can't just divide it out. So we're just dividing as much of the volume out as we can, and we can't divide out R, so we're leaving that in. Oh yeah, and by the way, this R plus delta R, that's because this surface, 2 pi L, 2 pi L is this surface. So like as R changes, this surface gets larger. So on the outside, say this is the outside, say this is R plus delta R, the surface will be like obviously this whole thing. And then if R is just regular R, it's just this. It's like it's smaller. So that's why those values are different, because it depends. The surface actually like depends on the surface size depends on the coordinate R. So that's why it's R plus delta R and R plus delta R. Yeah, but that ends up not really mattering, because if you R plus delta R divided by delta R is basically equal to R divided by delta R, because why is that? Because R divided by delta R, since delta R is like an infinitely small number, this is going to be a reasonably like incredibly large number pretty much. And then this delta R divided by delta R, that's just going to be like 1. So it's basically R divided by delta R basically equals R plus delta R divided by delta R. So that's why when we take the derivative of this, we just say R here and not any combination of R and delta R or whatever. So yeah, and a derivative is out minus in, out, or out value minus in value divided by out position minus in position. So this is correct, and then yeah, so that's why we move this to the other side, and it still retains that negative sign from here. That's because we have to flip the sign to get it into the derivative form, because this is in minus out, and for a derivative, it's out minus in. And in minus out is just the momentum shell balance type notation. So, yep, rho gr. Why do we have rho gr? That's because gravity in the radial direction. Because we're differentiating in the radial direction, the gravity is going to be in the radial direction, I guess. Is it GR or is it GZ? I don't know. I'll just leave it like that. It's probably fine. So yeah, we're just moving this to the other side, and it's going to be, this would normally be positive. This would be positive, but then you move it to this side. Like it was over on this side. It was positive. You move it to this side, it becomes negative. And that's because when you do the derivative operation, it switches the sign. And that's why they have the same sign with flipping the side. All right, boundary conditions. So first boundary condition is the law of the wall boundary condition. This is due to friction. And it's basically when you're in turbulent or laminar flow, the water or liquid moves at the same speed at the wall when it's at the wall. So, what is this? The liquid here will move at the same speed as well, and you can see that from this little drawing here. At the wall, the velocity is 0. And then second boundary condition at r equals AR, dvz dr equals 0. And that is because if we look at this drawing again, dvz dar is the derivative of the velocity profile. So the derivative is the slope of a velocity. Derivative is a slope of a function. So this this line here is kind of like a function map of the velocity. So the velocity is at a max here, and so the slope at a max is just a horizontal line, and the slope of a horizontal line is 0. So that's why dvz dr equals 0 at this point at AR. Yeah, AR. Radius equals AR. Yep. And yeah, that's maximum velocity derivative of 0. Yeah. Okay, so now we integrate. So yeah, we're just taking this function, separating and integrating. Yeah, the integral of dx is just x, so the integral of d this will just be this. And we're just doing regular integration here, indefinite integration. And the reason there's only one integration constant is because having one integration constant is the same as having two integration constants. Imagine an integration constant here. On this side, you can just add it over to this, and you can just conglomerate it into one constant. All right. So employing boundary condition 2. So we're employing the second boundary condition, this boundary condition, because we have dvz/dr available in this equation. Yeah, so second integration, we're oh wait, no, you don't have to do any of that with the UR, because it fixes itself when you have this integration constant. So no, this is right. This is right here. So yeah, so now you just plug C1 into here, and then you isolate the derivative, which I did here. And you separate and integrate. So separating and integrating. Yeah. So now we're employing the first boundary condition, which is the zero velocity boundary condition at r equals big R. Or, yeah, at r equals big R. So yeah, we just plug in r for little r here and for little r here, and we set vz equal to 0. And you can see that's what I did. And then we solve for C1, C2. And then we plug C2 and C1. Plug in C2 and C1 into the equation. Well, actually, we just plug in C2 because we already have this here. So yeah, you just plug in C2 into this, and then you'll have the answer. And yeah. So now we're simplifying it to match the given equation. So the equation is this. So one of the main things is you just look at like the conglomerate terms, and then you factor this out. You just factor this out. So do whatever you can to factor that out. And that's what I did. So yeah, just look at the given equation and just factor out like terms that it has isolated. And obviously if you're not given an answer, you won't have to do this step. You could just leave it like this most of the time, unless your teacher is kind of just not nice. this will probably be a fine answer. So yeah, so you use a log property. The log of r over big R equals log of little r over big R equals log of little r minus r. So yeah, that's here, and then you're factoring, and so this equals this, and then that's part A. So now for part B, obtain a mass rate of flow for in the film, and mass rate of flow is, let's see, mass flow rate equals 1 over A. The integral of V over dA. So yeah, so this is the average velocity here, and then you multiply that by rho, and the area. The area is the area perpendicular to the flow direction, and W, integration of average velocity of a plane perpendicular to flow direction. Okay, so yeah, dA is AZ. Yeah, that makes sense. Yeah, AZ is this. So this area extends in the perpendicular direction to the flow. So the flow is the Z direction, and AZ is the area perpendicular to the Z direction. So yeah, that makes sense. And we solved that AZ earlier in the problem. So just go back to that if you want. So yeah, this delta R is the same as dr. And the bounds are from AR to R, and that's because we are trying to find the velocity distribution in this area. So the area here is from AR to R. So, and AR is bigger, so that's the higher value on the integral. So yeah, just plug in our velocity equation that we got earlier into this equation here. And that's what I did. And this is 1 over A here. And that's from, what is that from? Oh yeah, that's the total flow area. So it's like, let's go to here. That is like this whole circle minus this inner circle here. So yeah, it's like obviously the area of a circle, pi r squared, pi AR squared minus pi r squared. So yeah, that's where you get that from, the area perpendicular. And that's in the area perpendicular to the flow direction. The flow direction is this direction. The area perpendicular to that would be like this area. So yeah, that's where we got that from. And it's 1 divided by that. So yep. Oops. So yeah, 1 divided by pi AR squared minus pi r squared. And then we're just taking out all of the terms that we don't need out of the integral. So any terms that you can multiply or divide out of the integral, adding or subtracting terms, usually it's not going to work. But as long as they don't have anything to do with r, if you can divide them or multiply them out of the integral, do that, because it's just convenient. Where does that 2 pi come from? Oh yeah, the 2 pi comes from the dA, so that's where the 2 pi comes from. And you could just take that out of the integral as well. And we're taking this term out of the integral. There's a 2 pi dr, and you have this extra r from the dA here, this extra r from the area perpendicular to the flow direction. So, and I don't know, this whole term is alpha, and these future calculations so I don't have to keep rewriting it over and over again. This is the correct integration, I want to say. Maybe. Hopefully. I don't know. It's just algebra. It's basically just look. After the expression, it's just symbol lab, Wolfram alpha. I don't know. Just figure out a way to do the math. It's just really this class isn't really about doing the math complete. Like, it's not about like learning how to do integration. So yeah, this answer matches the given answer. Pretty sure. Oh wait, there's not even any given answer. But yeah, that's the right answer. I just trust me, bro. Trust me, bro. This is the right answer. All right, so now part C. So the result in B simplifies to equation 2.2-21 if the film thickness is very small. Let's see what I have to say about that. All right, yeah, 2.2-21. Set A equal to 1 plus epsilon, where epsilon is very small. This allows you to use Taylor series and C 0.2-3. Only use the first four terms. Okay, so this problem's annoying, kind of. Taylor series. I think it's this here. Only use the first four terms. Alpha equal to that. Okay, so yeah, the ln alpha. So that's where that comes in. If you set alpha, or if you set A equal to 1 plus epsilon, and you go to here, you could say 1 plus epsilon equals epsilon plus this, plus that, plus that. And then that's what I do. And there's a previous problem that kind of gets you into this process, but I could upload that as well. I just haven't because it's an annoying problem. It's just algebra. It's just really just an annoying problem to do. So yeah, in this, I just convert this whole parentheses into setting alpha equal to 1 plus epsilon, and this ln A equal to that ln 1 plus epsilon equal to this from that table of the Taylor series. So yeah, I factor in the TI-89. Again, I could probably show a video on that, but I mean, I could also just link a YouTube thing. I might just do that. I'm not sure, or I might do a video myself. I don't know. Yeah, because epsilon is a very small decimal, probably number we can ignore. 1 e to the negative 14. So yeah, we could probably ignore that. And so we ignore all of these except for the biggest one because epsilon is a small number. And so eighth factor of a really small number, seventh factor of a really small number, sixth factor, fourth factor of a small number is going to be relatively small compared to the third factor of that same small number. So we just multiply 5.33333 infinitely to the third, and we multiply that times just this here. So it's basically going to be 5.33 divided by 8 times epsilon to the third, which I'm pretty sure is what we got. And 5.33 divided by 8 is 2 divided by 3, I think. Yeah, 16 divided by 24 is 2/3. Yep, that makes sense. And yeah, we get that for the mass flow. Oh, no, it's not. This is not equal to this. Cosine B. Okay, so we can say cosine B equals 1. Set W equal to 2 pi r. Width equal to 2 pi r. So yeah, set width equal to 2 pi r. So the width in this is analogous to the circumference in the cylinder. In the cylinder example, and we're just setting it to 2 pi r because, yeah, it's like the width of the surface. So we're setting W width equal to 2 pi r because width is perpendicular length that liquid flows on, and that's the circumference, is 2 pi r in our system. Water's flowing over and down the side of the cylinder. In 2.2, sigma represents where there is no slip boundary condition. It also represents film thickness. Does that make sense? Got the second expression, 2.2-22, to solve for it. Okay, so yeah. Sigma. So yeah, basically we just need to solve for sigma to get rid of it in our expression. So we're given these two equations. We just choose which equation would be more convenient, and for us that is probably going to be this equation here, the second equivalence, because obviously VZ, the average velocity, is going to be a lot of crap in it, so we just use the second one, I'm pretty sure. Yeah, so we just want to solve for sigma in terms of all this. Does that make sense? Solve for W earlier. Oh yeah, this is mass flow W. So I mean, I guess you can do average velocity too, since this is also a pretty big expression. But yeah, I'm just going to do mass flow. Cosine B equals 1 because it's a vertical line. So, or our cylinder is vertical, so the gravity is just going to be acting completely. There's not going to be any slant. And we're setting W equals 2 pi r again because we did that earlier. W equals 2 pi r because it's the surface that the water is adhered to. So yeah, here's just some canceling terms, and we say that sigma equals r times epsilon. So then we can plug in r epsilon into sigma. Where is that at? Oh yeah, so yeah, it should just be sigma cubed times r, because there's r to the fourth, epsilon to the third. It should just be sigma cubed times r. And yeah, 2 pi r. Does that make sense? Yeah. Yeah. That makes sense. Wow. Woo. Okay. And yeah, that's what we do. So W equals this. And this matches the equation that was on 2.2-22. It matches this equation. Yeah, okay. 2 pi r epsilon squared, and then you just don't have this here. Yeah, it matches. Okay. Yeah, that makes sense. Just W equals 2 pi r. And we get 2 pi r times this, and this equals epsilon squared. So yeah, that's the end of the problem. If you have any other problems that you would like solved, please leave a comment. If you have any suggestions as to how I can improve videos, please also leave a comment. Yeah, that's about it. Have a good day. Bye bye.